start process, and then it goes to the ready state. Start state, then ready state, then execute state. Just a revision. And from execute state, it can come to the IO or wait state, wait or IO state. And from there, it can go to ready state. Or from exec state also, it can come to the ready state by timeout. By timeout, right? This far we had discussed, right? Please say yes or no, otherwise I'll...
Yes, sir. Yes, sir.
Yes, sir.
You know?
Yes, sir.
So this is what we discussed in the last class. Now, we also mentioned that the operating system maintains a queue, one for the ready state, one for the wait state, right? And in this queue, there are entries. Now, last time I very loosely said that for example, I said that the rate process, which was in the execute, now at timeout, it goes to the ready queue, ready state, and the ready state, from the ready state, there was a green process which comes to the exec state. Like that I was discussing, right? And when it comes, this obviously goes. So I was discussing like this. But actually, does the process move? What is a process? The process is, you see, in my memory, I have got, just a minute. In my memory, I have got these programs, right, laid. This is program 1, or in my terminology, let me do it. Here was the green program. Here was the red program, and here was the blue program, might be. So these were there. Now these programs, one of them, right now in the execute state, the green program is there. So I was calling it the green process. And because this green is actually getting the access, Shubhrata Nandi is calling. Let me see. Yes, Shubhrata? I have started class, I think, but I don't know how many of them are there. So do you want me to come out of this link and re-enter the other link? I have started the class, but I do not know how many are there, or whether everybody could get in the link or not. Somebody can check how many participants. Anybody can check?
Sir, it
Sir,
was
105.
106.
1
105.
107.
Yeah, I'm continuing. Okay. Thank you. Okay, no, they are already in, so fine. Yeah. So actually, the green process, which is in the green program, is in the memory, and the green program, when in the CPU, it is executing and its state is changing, right? So therefore, we call it to be a process. Now, when that green goes from exec to ready because of some timeout, then we are actually not moving this piece of code. We are not moving this green piece of code physically anywhere, right? What we are doing, because that is, where should we move it? Because somewhere in this memory, somewhere the ready queue is also in the memory. Any data structure that I am using for the operating system to run is also in the memory. So I am not moving this program from here to here. Is it clear? I am actually creating these entries. Now, what are these entries? the entry. So let me erase this. So now I represent one queue, any queue. Let's call it the ready queue. Yeah. The entries of the ready queue are nothing but the process control blocks. Process control blocks or PCBs corresponding to each process. And what is there in the process control block? A process control block has got a number of entries. It is again a data structure, just like a C structure. All right. It has got a number of entries, records or fields. For example, you will have all the register values. The registers of, right now let's talk about the green process. So every discussion we do is with respect to the green process. So registers of the green process, register values of the green process, okay, are stored here. Now, this is the PCB of the green process. Also, we have the program counter value of the green process. Why is that needed? Because you see that from the exec state, it had come down to the ready queue, ready state, and sometime later, it will again get hold of the CPU when its time comes, and it will go in the CPU. At that time, from which point should it start its execution? That's why we need to remember the program counter value as well. We will also store all the files, open files that are there in the green process, all the files that were open, all those things will be here. In that way, and there are registers I have already said, program counter, open files, and some other data, whatever you need, the procedures and everything, all those things are stored in the program counter, process control block. Similarly, for the read process, say for example, I will have another PCB where that is the PCB for the read process, which will be somewhere here, which will be very similar to that. So these structures, or now where are these? You should understand. Where are these things located? Some of you can tell me. Where are these?
Memory.
In the memory. All right. Very good. So here are also the PCBs, say PCB red, PCB green, etc. So what should I store here? Can you tell me? They are already there. Now in the ready queue, what should I store?
Sir, the starting address of the
Pardon? Yes.
starting address of the PCB.
Absolutely so. But can you tell it otherwise? Other words, I'll have pointer to the PCB, right? I'll have pointers or addresses to these PCBs. So my ready queue, I can now express in different ways. My ready queue is a queue of pointers to PCBs, or in other words, I can also say that the ready queue contains the PCBs. Now, everyone can say, will you physically move so many items? This, all these items will move every time. No, we'll just shift the point. Right? That's very clear. Your computer science students are very simple. So, actually, we are having the process control blocks, their corresponding information stored in this queue. And so I have got one ready queue and one wait queue. So let me proceed. Is the concept of PCBs clear to you? We'll come back to that again when we need it. Is it okay?
Yes, sir.
Okay. Oh, anybody has got any doubt? All right. So,
Sir, I have a doubt.
yes, Chodashia,
Uh,
right?
yeah, yes, sir.
Yeah, go on.
Sir, in the middle of a process, if we need to stop it right now because of
Yeah.
some IO interrupt, sir, we
Hmm.
need to store the machine states, right, sir?
Machine states means what?
The state of the processor at which we stopped it.
The state of the processor.
Sir, the states of the, what do you call it, sir? Uh,
What do you
the
call it? That
machine.
is the million-dollar question. You're right. So basically, what say? Okay, um, let me bring you forward. Now, what Dhiraj is saying that at the let me draw something that a program was in the execute state, right, Dhiraj?
Yes, sir.
So where is it running? There is my CPU box, all right, with all the ALU and everything inside.
Sir, actually, we can't see the presentation, sir.
Oh, sorry. Okay. Um, yeah, you can see it, right? So you can see it now.
Yes, sir.
So this process, say the blue process, was running inside the CPU. Now there has been an interrupt. Interrupt is a signal that has come to the CPU and that has pushed it back to some state, right? Uh, whatever state it is. Say it's a timeout interrupt, so it has come back to the ready state. Now that means what? The inside this, inside inside this CPU, there are registers, right? These registers were holding the value of which program or which process?
Blue, sir.
Blue process. Now, what I have to store when I push out this program, what I'm actually, I means the operating system, all right? What the operating system is actually doing is pushing out the program from this CPU, as if CPU is a house and a guard comes and pushes you out of the house, and you are going to another house or another queue. Okay, what is happening? Yeah. My God, what happened? I probably, yeah, I probably placed something wrong, so it vanished. However, um, yeah, I think yes. It is there. So it has been pushed out. So when it got pushed out, it cannot leave its half-cooked fish, half-cooked sabji in that house because you have been already thrown out of that house. So what we will do, we will store that somewhere. But I'll again cook that from that point onwards when I come back. So where do you store them? You store them in a stack. In a stack, all the register values, the program counter value, open files and everything. And that, all those information together, you are putting in the process control block. Therefore, the process control block contains everything. When you come back again, your state changes from maybe ready again to execute, and you start cooking again. You again reload these places with the old value. Am I clear?
Yes, sir.
Okay. All right. So that is how interrupt is processed. Now let us start. You'll all become computer scientists, so or computer engineers. So one question that people can ask you, and I certainly ask in any uh, selection or anything. You are a computer science student, so when you put on the power of the computer, of your laptop or of your desktop, what actually happens? What actually happens? Anyone can tell me what happens? As you put the power on, what happens?
So first, there are some technical checks that all the hardwares are working properly or not, that post test, and then OS is loaded in the primary memories.
Very good. Very good. I just like to change your statement a little bit. Not the entire OS is loaded. Only a segment of the OS is loaded in the main memory. Okay? Because OS is a huge program. So the entire OS we do not need. So the entire OS can peacefully remain in the secondary memory. Okay? Only the relevant part is taken. So in that, very good. In that OS, first an initialization program starts, which initializes the system. Then a login program comes. I think Professor Subroto Nandi has talked about this init, or he will talk about this init in the context of Unix. It's always better.
Yes, sir. I've already done that in one of my classes.
Yes, fine. So it comes to the login. And at that point of time, we get this login prompt. In Unix, we get the dollar prompt, say, in Bone Shell. And then I type cc, say, myproc.c. The meaning is obvious. I want to compile my program.c. So after login, the operating system is in a state which is the command interpreter state. CI I am writing for short, command interpreter. So at that point, I am writing this and it's waiting for the command. This is operating system waiting for the command. So as I type in CC, suppose instead of CC, I would have written PC or SC. Then that would carry some other meaning, if at all. Otherwise, it will be a bad command or file name. Right? It's a meaningless thing. Otherwise, it's a meaningful thing, CGUI. Then this command interpreter will invoke the C compiler and will pass on this myproc.c as a parameter to this C compiler. And after this compilation is over, if there is some error, then again I'll come back to this command interpreter point, and again we'll get this dollar prompt with some error messages. If it is successful, then fine, I'll come out, and also then without any error messages, I'll come here, and then I can give my execution command or whatever. Similarly, when I was editing, let me remove some of the lines that I won't need. Now, if at the time of editing, when I wrote myproc.c, that is earlier, before this CC, I had written vi myproc.c maybe, right? So at that time, from here, I had invoked a vi program, which is there in your friend who said that the operating system is brought in the memory. Maybe the vi was not brought, but when this vi is required, then that vi program is brought in the memory. Okay, so this is how it goes on. After vi, again I go back to the command interpreter, and it goes on like this. So now let me draw an onion structure of the operating system. And I'll try to relate. At the very core of the system, this black part is the hardware. And around the hardware, I have got here, this part, I call it to be the kernel and device drivers. I'll come to that. Okay. Above that, I let me select the data. This is the shell. And this command interpreter is nothing but this shell. All right. all the shell commands that we give, we often say we are dealing with shell commands. That's nothing but the command interpreter. And around that shell, we may have some systems programs lying, like the compiler, like the VI, maybe the database management. Although it's not looking like an onion because of my bad circling, but you can have a better circling. And at the top of all, we have got the application layer. That means whatever application we write, that is running. Now, let's look at that thing again. What I wrote there, $cc myproc.c. So when I gave that from the command interpreter, so I gave that command here, and it should call the CC. And where is that CCC compiler? Inside which layer? The green layer. So the command interpreter should call the CC, which is here, is a CC program here. And the CC should start running. Am I clear? Am I
Yes,
clear?
sir.
Yeah. But that is not that doesn't happen. And there is a specific reason that I'll be explaining today why that doesn't happen. So what happens is actually something different. That is, I gave the command, I means now here I am the user. I gave the command CC, and that has been accepted by the shell or the command interpreter. Now the command interpreter finds that it's a valid command. Okay. Now it will invoke the CC, but before that, it will take the support, assistance of the kernel. It will come here, and from there it will invoke CC, and not in this direct form. Why is it so? Why does the CC, with any utility, say command, anything that is any operation, or if any operation that is involving some systems layer, has to go through the kernel. Has to go through the kernel. Why? That is the question that we are trying to answer now. Is the question clear to all of you? That
Yes,
when
sir.
the shell got the command CC and it knows that the CC is there, why don't I directly execute CC? Why do I come to the kernel and through the kernel I invoke CC? That is the question that we are trying to answer. Before that, let's keep this suspended a little bit. Before that, let us talk about a couple of terms like multiprogramming, multiprocessing. I am not talking of multitasking right now. I'll talk about that later. And time share. Now you see, multiprogramming we have encountered already in our discussion. So some program is running, let's see, and you can now relate. So here is a CPU. And some program, let's say, the green program is running inside the CPU. This is a CPU. Now, this program now requires an I/O, and there is some I/O device here, some printer device here. And the CPU can, one option was that the CPU actually works with this printer and starts printing. That means the CPU will remain busy because printer is a slower device. But I have got in my ready queue the other processes like blue and red waiting in the queue. Blue and the red are waiting in the queue. So what is done instead, I can have just as another piece of hardware that is say which is a IO processor. An IO processor is similar to a CPU, another processor. Say, assume that it is another processor, but the instruction set of the IO processor is not as rich as the CPU. So now what can happen is that the CPU, when it sees that this green program needs to have something printed, what the CPU can do is it can simply communicate with the IO processor and tell him that, okay, this is the green program, its address and everything is told here. And also what it does to do, what it needs to be done is the printing. As soon as it does that, then this is free. Mix of colors. So now this is free, and so now the IO processor. What am I doing? Now the IO processor is actually communicating with the printer and printing. And what happened to the CPU? It is now free, right? Because this will take, say, maybe 100 milliseconds. In the meanwhile, I can process many things, and I can make this blue process come here and be removed from the queue, and now the blue is running. So what is happening here? The green is in the IO processor mode, and the blue is in the execution mode. Is it clear?
Yes, sir.
Sure.
So tell me, in terms of our process state diagram, in which state is the green? In which state is the green?
So
It's in
wait
the wait
state.
state.
Wait state. Absolutely. Others should also answer. And in which state is the blue?
Execution.
And in which state is the red?
Ready
Ready
state.
state.
Fantastic. So therefore, what is happening is, you see, let me erase all of this. If I draw a time chart, I can draw it like this. These are the time cycles. At this time, during this time, the green was executing. Let me see. This is about the green. Green was executing. So this is the CPU state, CPU line, and here is the IO line. At this point, the green started its IO and is no longer in the CPU. And who is in the CPU now? In terms of our last drawing, who was there? The blue. Now the blue will be in the CPU state, right? And so this is not. Oops. All problems. Yeah. All right. So if I take a snapshot of this point, what do I see? How many programs are running? Huh?
So two programs.
Two programs are running. But how can two programs run in a uniprocessor environment where you have got only one CPU?
So one process is running through the IO part, and one is running through the CPU part.
Absolutely. So actually in the CPU there is only one process running, and In the IO, another process is running. So from the top, if we look at, we can see that, okay, both these are, none of them are in the red and blue are neither in the finished state nor in the ready state. So they must be executing. Okay. So this scenario is known as multi-programming scenario, where multiple programs are as if working together. Now, then what is multiprocessing? Multiprocessing is the scenario where I have got multiple processors, CPUs, okay? So processor PR, processor 1, processor 2, processor 3, and I can have multiple IO devices as well. And I have got a global memory. Right now I'm assuming the architecture where I've got a global memory, which is accessible by all these processors through a bus. And each of these processors may have their local memory. These are their local memory. LM1, LM2, LM3. All right. And these processors are interacting with this global memory through this bus. And obviously, when more than one are trying to communicate, we need some sort of arbitration mechanism over this bus, allowing anyone. So at any point of time in this architecture, what can happen? At any point of time, it's possible that in one processor, the green is running, in one processor, the red is running, and in one processor, the blue is running. All right? In the memory, all these are loaded. Here, maybe the green, here the blue, here the red, and here the green, maybe. Okay. So all of them can run at the same time. So this is known as multiprocessing. So in a multiprocessing, obviously you have got multiprogramming, but the converse is not true, that all multiprogramming scenario are not multiprocessing scenario. Okay, clear with you?
Yes, sir.
Yeah. So now let's, any question? Any question, anybody? Are you there? How many of you are there?
Yes, sir. We are here.
I'm not getting any female voice today. You have stopped coming to the class after yesterday? Anybody present?
Yes, sir.
Oh,
Yes, sir.
very
Yes, sir.
good. Very good. Now we are coming to
Yes.
the last one, which is the time sharing. All of you know that, right? In your lab or everywhere, what you do is, we have got a number of terminals. And you are sitting in those terminals. But, say, I have got only one server here. And let me assume that this server that is there has got only one CPU, not more than one CPU. And there is only one copy of the C compiler. Now all of you sitting here are running your C programs. And all of you are getting the response from the computer, right? Of course, all of you are connected to the LAN, and I'm not showing that you are connected, and the entire thing is connected with this, everything is there. Now, here you are typing something, he is doing VI, he is doing CC, he is doing /a.out or whatever. Now, all these things are being responded to. How is that possible? By one CPU. It is being done through one CPU by time sharing. That means each of these are processes. Your CC is a process, VI is a process, A dot out is a process, and all of them are allocated a fixed time quantum. By the operating system. And suppose that time quantum optimally it is 5 milliseconds. So for 5 milliseconds, this is numbers, roll number 1, roll number 2, roll number 3, roll number 4. Roll number 1's process is executed. If he has got IO, then fine. He goes for IO. Let him come back again. But if he is in the exec mode, even after 5 milliseconds, even then, after 5 milliseconds, he is pushed out. Okay. And this guy, roll number 2, gets the CPU. Then roll number 3 gets the, or roll number 3 is absent today. So roll number 4 is getting this. In that way, everybody is getting a particular segment of time, and that's why it is known as a time sharing system. Okay, clear? Can you move forward?
Yes, sir.
Yes, sir.
Yes, sir.
So now we again revisit what we did in our process state diagram. We had so and so things, and we were in ready here, and we were in exec, and wait was there. But from exec, we had a timeout. And this timeout, in my last discussion, I said that after every 5 milliseconds, the program, if it is not completed, if it doesn't go to the finish, it is pushed back to the ready queue. All right? It's pushed back to the ready queue. And so my ready queue is here, and roll number 1 was at the head of the queue, and roll number 2 was here, 3 was absent, and 4 was here. So 1 went to the CPU and was executing, and then 1 again rejoins this queue here. And when will it again get access? After 5 and 5, after 10 milliseconds. Again, 1's turn will come. Because this will get 5 milliseconds. Within this will get, actually this is, this means, this number 2 will get 5 milliseconds, right? Now this may complete, maybe within 2 milliseconds it will complete, finish. Then obviously this is cleared up. And suppose it takes, this one takes, it's a longer program, number 4 is a longer program. It takes requires 10 milliseconds. So after 5 milliseconds, this will also be pushed out, and it will go back here, and leaving aside this. And so again, 1 will get the time. So 1 will get the time in this case after 7 milliseconds. Is it clear, this timing?
Yes, sir.
Yes, sir. Yes, sir.
I think if somebody is having some doubt. Huh? Now, I'll continue today for another 15 to 20 minutes. Is that okay with you?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
All right. So that is what the timeout is doing, and without the timeout, our time sharing system would not be effective. Yeah. Now, as I was discussing in the last class, this timeout is implemented by a timer. And for this purpose, let's assume, although we can implement a timer in software, but let's assume that we have got a hardware. Hardware is actually a hardware timer is allocated to the operating system for this purpose. So as I think said in the last class, that as soon as a program is this red program is coming to this exec state, then and there, this timer is set to a value 5 milliseconds, say. And it starts counting down. It starts counting down. As soon as it becomes 0, it sends an interrupt to the CPU, which stops and sees that it's a timer interrupt. And that means the current process, which was sitting in the registers, everywhere, the program counter, all those things have to be saved. And we have to decide which program should go next. So who will decide that? So this is a very critical point. Let's think together. The red program was executing. Timer started. Timer is over, 5 milliseconds over, an interrupt has come. Hardware interrupt. Immediately, the execution stopped. Timer se aaya, interrupt, so it will be stored in the, all those status will be stored. And then, the next process which will run in the CPU has to be chosen. Who will choose that? Tell me, who will choose that? Anybody? Who is taking these decisions? No one? Have you left the class? Hello? Am I audible?
Yes, sir.
Voice?
Tell me.
Yes, sir.
Who will have to take the decision?
Sir, voice?
Absolutely.
The OS, OS.
Let there be a wrong answer. Doesn't matter. But OS is the correct answer. Now the OS is a software. So how can it take a decision? In order to take a decision, the OS will have to execute. Am I right?
Yes, sir.
Yes, sir.
And where can OS execute? Where can a program execute?
In the
Execution.
CPU.
CPU, sir.
In the CPU. So the OS gets control of the CPU and decides, looks at the data structure and decides which program should execute now. And that may be the blue program. So that is decision is taken and the blue program should start running. Now you have to tell me something more. Where was my CPU? The CPU was somewhere. Let me draw the CPU here. Let me draw the CPU here. Now CPU had a program counter and that program counter was loaded with the red, right? Now the timeout has happened. Then here the red program, the red program was capturing the ALU or whatever. Now the timeout has occurred. Now PC is loaded with the program counter value of what? Which program?
Sir, the
So
OS.
the next program which is to be loaded.
No, Mr. Smith.
OS.
Yes, it will be loaded with the OS. Say OS is green. So OS is program counter, and OS runs here. This is gone. This is gone. OS is running here. Now OS has decided that okay, now the next candidate is the from the ready queue, the blue program. So now how can it make the blue run? How can the OS make the blue run?
Sir, by setting the program counter to blues.
The starting address of blue. Absolutely. So the program counter will now be loaded with the value of blue. Now, how, you can ask, how is that possible? So the operating system has got a particular module, will be discussed in much detail later, which is known as a scheduler, which is a program. And this scheduling program will have an instruction. I'm just giving some, say, LDPC with the blue program counters value. Suppose this is an assembly language program statement. Say the scheduler executes an LDPC blue. LDPC blue, load program counter with blue, and then this program counter automatically comes here. All right, and then you take your hand off. Clocks will come, and which program will start executing?
Blue. Blue.
The blue program, don't sleep. Yes, the blue program will start executing. That is how the timeout is implemented by a timer, and this is how the time sharing system works. So you must. I don't want to drag you any further today, but let us revise quickly. The very critical things that we have talked about are interrupts, detailing. We'll do in the next class. I'll not load you today with that. You need to digest this. So you can see that a very critical thing that you have learned today is the operating system is nothing but a high priority program. So that will also have to be treated just as a program. Any program cannot execute without getting inside the CPU. So the operating system also cannot get anywhere without getting inside the CPU. So whenever in between, so let me draw another diagram. So here was a execution that was happening for a red program here, and when the green program starts, say I say that the green program starts here. In between, the CPU decided the OS has made an execution. The OS, let me make it red. The OS has worked here, and the OS decided that the next one is green. Therefore, next one is green. So that green would go there. So here, everywhere, there is some user process, then OS, then again user process. Now this OS part I was talking about, this OS part, now OS I had shown that it has got so many layers like this. Now this OS part is not the shell part, it is the kernel part. I'm sorry. It is the kernel part. The kernel of the OS takes care of all these decisions, and that's how it goes on. Last time I told you, are you too tired? 5 minutes more?
It's okay, sir.
Yes, sir.
Yes, sir.
Huh?
Yes, sir.
Yes, sir. Yes, sir.
Yeah. So I just complete with something I said. I said that when this CC was being executed, then it was taken by the shell, and the shell then went, what happened? Yeah. Something happened. They're not allowing me to continue. Let me start again. So let me. So we had the shell, and the shell was going to the was first calling the kernel, and from the kernel we are calling the CC. That's what we say. Why did I say that? The reason is, say for example, roll number 1 is here in this terminal. Roll number 2 is in this terminal. Roll number 3 is in this terminal. It may so happen that this roll number has given us CC. At the same time, this roll number has also given us CC command. And there is only one port C compiler. There is a C compiler, actually CC program. I mean C compiler program. Now, CC some text, and CC some text. Now, when it comes, if the shell had directly given the control to this CC, the C compiler, then it will be compiling for this for a while. In between, this will come, and you also ask for the C compilation. So the things could be interleaved. A better example would be, let's see that both of them have given a request of a printing. So this has also given print, PRT, I'm just writing for space, print. Now, I've got one piece of printer, and in one piece of printer, say this here, I have got a blue file, and here I've got a red file. If there be time sharing between these two, and both of them are doing, then what will I get? I'll get a red line printed, 2 red lines printed, then one or two blue lines printed, then again 2 red lines printed. It would be interspersed. That's not what we want. So here is a situation where we have got a scarcity of resource, that is a resource that is shared. A resource that is shared between multiple processes. So, when a request comes from a particular process for a shared resource, a C compiler or maybe printer, whatever it is, the shell cannot directly give. Suppose you are the shell, all right, and I am the resource manager sitting at the back, and I am the storekeeper actually, and I have got only one piece of key, for example. Now, you cannot directly give that to him. If you had multiple copies of those key, you give it to them, and then the entire thing will be like this red, this sort of printing. Instead, it's a layered approach. So what can happen is when a process asks for some shared resource through the shell first requests the kernel, which also has got the device driver or the resource manager, and it decides whether that resource is available. If that resource is available, it goes over there, and then only it can be given to that person. That's why any program statement, any execution of a program is divided into 2 different modes. We'll discuss that in the next class when I take it. Operating system operational modes. One is the user mode, at which normally the user programs can execute, and the other one is the supervisory mode, supervisory mode or the kernel mode, you can call it either, where the overall supervisory decisions are taken. At that time, you see, if I draw the user here, let me just put the user here. The user is actually interacting with the user mode and cannot directly go into this, into the supervisory mode. We need some ways and means by which we can switch between these two modes. The user's interaction is only with the user. That is required for a number of reasons, for privacy and many other things, which we will take up in the next class. I'm giving you a quick 5 minutes or 3 minutes for placing any query that you have right now. You can later on think of other queries and let me know. I'm stopping sharing. Now tell me. Yes.
Sir, mm, sir, you told the PCB is stored in the main memory, right?
Because you have got no other place to store.
Okay, sir. So the timer, the CPU timer is about five milliseconds, right, sir? So when we need to push out a process, then we have to access the PCB once again from the memory, right, sir? And that is gonna cost some time to the CPU.
Yes.
Sir, so isn't it reasonable to dedicate a hardware resource for storing PCBs?
That will be too costly. How much hardware resource will you do? But actually, what you are saying is right. See, let's again, let me share the screen once again. Very good question. Where is prison now? Enter screen. Let me do this. So in my memory, remember it is not a secondary memory, right? So it's a primary memory. Somewhere in the primary memory, I've got my PC. I'm not, by the way, Dhiraj, I'm not moving the PCB at all. I have got a ready queue somewhere here. This is a ready queue.
Sir, the screen is not shared, sir.
Oh, it is not shared. Why not? I just not shared. Oh, sorry. Is it shared now?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So the ready queue is here somewhere where you have got all these entries. So you are actually, and here is your CPU. Huh? And the CPU has got its own, please excuse my drawing, it's very bad. More so on these new devices. The registers are there, the program counter is there. So this is right now, say this particular process, which is PR2 maybe, is being scheduled. And so I have got a pointer to this location, PR2. Am I right? Now, whatever values are there in this, those are simply being moved to this register. So it's a memory to register movement. There is no physical movement in that. It's a register to memory movement. So whatever is the delay, that is the delay. All right. So in that way, you were right that when I had drawn that here is PR1 executing timeout and PR2 is executing here, PR2 is executing here. I had drawn the operating system in between, but actually the operating system should be drawn with some delay. Let me give a little more delay to make it visible. The operating system should be active here. Again, should be active with a particular delay. So this part is certainly This part is a delay, a time that is lost, and this has got a name, and that name is context switching overhead, or context switching time, or context switching overhead. All right, this much time I'm losing anyway. Now, how fast we can do that, that depends on the speed of this, how good the good quality this memory is and everything. Okay, so here, yes, you're right that I'm loading this. Loading this means I'm not moving them. It's a register to memory transfer. Sorry, memory to register transfer. So that depends on the CPU cycle, CPU clock, and the access speed of the memory.
Sir, I was just wondering if there is any cache involved, sir, because it seems reasonable
Yes,
to.
see, that's also a very important question. All through my discussion, I have assumed a two-layer memory architecture just to make it simplified. Secondary and primary. If you have cache, certainly many of these things can be kept in the cache, provided the cache size is good enough. You're right, absolutely right. But that is your engineering decision of the operating system. And when the operating system is generated, so whenever you buy a PC, it comes absolutely raw, right? And you have to load the operating system there, right? Now, when you load the operating system, what is actually happening? The operating system is configuring itself depending on the. I want to see. Can I stop sharing? Depending on what is the configuration of the hardware. If there is cache, the system will configure with some relevant parts put in the cache, some parts in the primary memory. If there is no cache, then it will do it in the primary memory. That is called the operating system generation. All right? Okay?
Okay,
Any
sir.
other question? Any other question? Should I assume only Dhiraj was attentive, others were not?
Sir,
Yes.
in multiprocessing, can the multiple processors access shared memory?
Yes, that's what I had drawn. The diagram that I had drawn, all the processes were accessing one common global memory. Are you also taking notes on your paper? The things that I am drawing, Prashun?
Yes, sir.
So if you look at that, you will see with every processor, I have drawn a local memory. Have you seen that?
Yes, sir.
So it takes its relevant data in the local memory and works as much as possible from the local memory. And when it saves something and writes back, because the processors may be running programs which need to communicate. That's another interesting part which we will discuss later. That then they will have to write to the global memory or shared memory. But typically, this is known. Okay, so let me once again share my screen. Is it shared? Can you see that? Yes or no?
No, sir.
No,
No,
sir.
sir.
No, sir.
What is happening? What is happening? Says, oh, okay. Sure. I'm missing the algorithm. Okay. So what happens is, here is a situation where, excuse me, here is a situation where we have got one piece of memory and a number of processors, PQR, are all sharing the same memory. Although they have got local memory, ultimately the thing is shared in the shared memory. This is known as a tightly coupled system. You're in which year? Second year or third year?
So third year.
Third year.
So in computer architecture, you have done. So it will be a tightly coupled, it's a tightly coupled system. So when there is a tightly coupled system, obvious the question is, what is therefore a loosely coupled system? The loosely coupled systems are essentially the distributed systems where, let me erase the whole thing. A distributed system is process P has got its own memory, MP, process Q having its own memory, MQ, process R is having MR. So they are all independent in like a distributed system, or when you talk about saving things in a cloud, they only communicate, these communicate only when required. That is done by some process called message passing. I'm sure we'll be having time to discuss this. Okay, inter-process communication. We'll do that. Okay, message passing. And the other thing I'm just mentioning, in a tightly coupled system, often we call it a broadcast because broadcast can be in this system also. Broadcast means when P sends something, it can be listened to by everybody. So in a bus-based system, if I have got this PQRs here and the memory is here and I send the data over the bus, over the common bus, then obviously all of them can listen to this. This is a tightly coupled system and this is a loosely coupled system. So in a multiprocessor environment, it can be either way, but typically when we talk of multiprocessor systems, we are talking of tightly coupled system, each having, I mean, they are being connected to a shared memory. Okay? Is it okay, Prashun?
Yes, sir.
So thank you very much for today. And if there are any questions, you please write it to me. Email to Professor Nandi or Professor Dotto, and I'll get them. All right. Thank you.
Okay, sir. Thank you, sir.